Welcome to the Explainer. Have you ever looked at a simple glass of water, a spool of wire, or even the fog rolling over a hill and wondered about their fundamental building blocks? Well, today we are breaking down the exact structural roadmap used by scientists to categorize the entire physical universe. But before we start categorizing, we really have to ask ourselves this big question. How do we actually make sense of literally everything around us? To do that, we need a rigorous system. Basically, a structured roadmap to decode the universe and determine the true identity of any given substance. Everything you can touch, see, or interact with is matter, but it's clearly not all the same, right? We need a way to look at any substance and follow a logical path to figure out what it actually is.
Okay, let's dive right in. Our agenda for today mirrors the exact scientific categorization process we're about to explore. We'll be mapping out matter, exploring pure substances, looking at the laws of composition, navigating the world of mixtures, categorizing complex mixtures, and finally, getting ready for the lab.
Let's jump into Section 1, Mapping Out Matter. Think of this flowchart as your ultimate master key. Whenever you encounter a new material, you start right at the very beginning, matter. The absolute first crossroads you hit asks, can it be physically separated? If you can physically separate the components, say by filtering it or boiling it, you follow the yes path over to mixtures. But if you can't separate it physically, you follow the no path straight down to pure substances. It's a brilliantly simple binary way to start classifying the immense complexity of the physical world. Moving along to Section 2, Exploring Pure Substances. If we travel down that no path of our flowchart, we arrive at substances that absolutely cannot be chemically decomposed any further. We're talking about elements, which are composed of just one single type of atom. Copper wire and aluminum foil are perfect everyday examples of this. No matter what chemical processes you try to put that copper wire through, you simply cannot break it down into something simpler. It is fundamentally purely copper. The exact same goes for the aluminum in that foil. Elements are literally the most basic, foundational ingredients of our universe. But what if it can be chemically decomposed? Well, then we get a compound. Take table salt, for example. In a compound, two or more elements combine in a fixed ratio, creating properties that are totally different from the individual elements themselves. Table salt, or NaCl, is made of sodium and chlorine. On their own, these elements behave very differently than they do together. But once they're locked together in a rigid, unchanging ratio, they lose their dangerous individual properties and become ordinary, everyday table salt. Next up, Section 3, Laws of Composition. So understanding how these elements actually lock together requires looking at the rules of the game. It really boils down to two laws. The first states a specific compound always has the exact same ratio. The second shows how mixing elements in different ratios spawns entirely new compounds. The law of definite composition ensures that water is always H2O and salt is always NaCl. It's totally fixed. But the law of multiple proportions, that's where things get creative. It proves that you can take the exact same elements, combine them in a new ratio, and build something with completely unique properties.
This concept is brilliantly illustrated here. Take one carbon and one oxygen, and you get carbon monoxide. But add just one more oxygen atom, and you get carbon dioxide. Two entirely different things. Just by changing the proportion from one oxygen atom to two, you go from carbon monoxide, which is a highly dangerous gas, to carbon dioxide, the gas we naturally exhale every single day. The building blocks are identical, but that ratio changes absolutely everything. All right, on to Section 4, the world of mixtures. Let's rewind our map back to that very first crossroad and take the yes path. This drops us right into the world of mixtures. Unlike compounds, mixtures are a variable combination, meaning they can be physically separated. And this brings us to a new crossroad. Is the composition uniform? Because mixtures are variable, they aren't locked into those rigid ratios we were just talking about. You could, for instance, evaporate the water out of salt water to get the salt back without breaking any chemical bonds. But to categorize them further, we have to look at how well they're mixed. If it's uniformly mixed throughout, like a solution, it's a homogeneous mixture. If it's not uniform, it's heterogeneous.
Which brings us to Section 5, Categorizing Complex Mixtures.
Now, if the composition isn't uniform, we break down those heterogeneous mixtures using a few key clues: particle size, settling, and the Tyndall effect. The Tyndall effect is kind of like a built-in detective tool. It dictates whether the particles in the mixture are large enough to actually scatter light. Solutions, which are perfectly homogeneous, have very small particles that don't scatter light and never settle out.
But on the heterogeneous side, colloids have medium-sized particles. They don't settle at the bottom, but they do display the Tyndall effect, meaning they scatter light. Suspensions, on the other hand, have large, chunky particles that both scatter light and eventually settle out if you just leave them alone. Let's anchor all of this with some rapid-fire real-world examples to see how this roadmap categorizes everything from your pantry staples to the weather outside. Graphite? That's a pure element. Sugar? A chemically bonded compound. Soda is a perfectly uniform solution. Mayonnaise and fog? Those are colloids. They scatter light, but the particles don't settle. Muddy water is your classic suspension. Leave a glass of it on the counter, and the dirt is going to settle right to the bottom. And pepper is just a standard heterogeneous mixture, where you can easily see all the different pieces. Every single piece of matter you interact with fits somewhere on this map.
Finally, Section 6, ready for the lab.
Understanding all of these classifications is incredibly important because it's the very foundation of actual lab work. But before you start experimenting with these substances, you have to master safe equipment handling, like the step-by-step procedure for safely lighting a gas burner. The sequence here is absolutely crucial. After adjusting and attaching the hose, you must always light your match before turning on the gas. Bringing an already lit match to the burner prevents gas from pooling up in the air, which helps you avoid a really dangerous flash. Just like our flowchart, physical chemistry requires a strict, logical sequence. So, what mysterious mixture will you decode next? Now that you've got the map to navigate literally all matter in the universe, just take a look around the room you're in right now. What are you really looking at, and how would you separate it? Is that coffee sitting next to you a perfectly uniform solution, or is it a colloid? Is the metal on your desk a pure element, or a compound governed by the law of definite composition? The next time you grab a drink or look at the everyday materials around you, I challenge you to crack the case. Keep exploring, and I'll catch you on the next one.